the formula for beta hat FGLS, beta hat GLS was really, you had this is the formula for beta hat GLS. Yeah, this is the formula for beta hat GLS. Because you use instead of x, you use x star, instead of y, you use y star, and so on. Right. Sure? Now, if I substitute my, this is GLS, this is not FGLS, so this is sigma I. This is nothing but summation xi upon sigma I minus summation 1 upon sigma I xi upon n x star bar, right? Yeah, whole upon this is the GLS. But do you see that if all the sigmas are identical, this is just the OLS formula? Do you see if all the sigmas are identical, this is the OLS formula? Because what will happen? If all the sigma i's are the same, then 1 upon sigma I would come out of this, 1 upon sigma I would come out of this, so 1 upon sigma I would be here, 1 upon sigma I would be here, so 1 upon sigma square will be outside, 1 upon sigma square will be outside here, 1 upon sigma square will cancel, and we get the OLS formula. Right? So this formula allows you to find beta hat when the variance of the error terms are different. So in that case, in that sense, it's a more general form. That's why you also call it the GLS, generalized least square, because we are deriving it under a more relaxed, more general set of conditions, that is the variance of all the error terms is not necessarily the same, it has to change. If it is the same, then you get the OLS formula from this. If it is the same, you get the OLS formula from this. If it is not the same, then you use a different formula, the GLS. Right? Of course, both would be unbiased and consistent as long as xi and p is not equal to 0. Covariance xc is not equal to 0. Now, how will you make the beta hat FGLS in this? How will you get the beta hat FGLS? Exactly. So by now you have estimated sigma hat I, no? So instead of this, put a hat. Right? Estimated this, so you get beta hat FGLS. Right? You get beta hat FGLS will be obtained by this. How do you get alpha hat FGLS? How do you get alpha hat FGLS? You will get variance of the error term. What will be the standard error of beta hat FGLS? It would be triple B variance of beta at FGLS will be sigma square V, and this is an estimated value, right, upon summation xi star, yeah, right, variance of beta at FGLS, and have we obtained sigma hat square E? Yeah, I put a dash here, okay? I put a dash here. I put a dash here to tell you that Ei hat dash is from this equation, right? Which is y star hat, right? Yeah, where alpha hat plus beta hat xi, right? Alpha hat plus beta hat xi. Sure, so we will be using, so to form the t values, for example, then we will be using these. So the corrected standard errors, right? These are the corrected standard errors. Okay. Now recapitulate this for me. You have got two or three steps involved. So if you want to do an FGLS, what do you do? What's step 1, what's step 2, what's step 3, what's step 4, and so on. या अभी पढ़ा ना अपन ने. Who can tell me? कैसे करेंगे? How will you do it? Any ideas, folks? कौन बोलेगा? Say something. Yeah? Right. Okay, so Ronak says the first step is to find E hat I. After that क्या करने का? Who will tell us now? E hat I मिल गया कि उसके बाद क्या करेंगे? या E hat I स्क्वायर करेंगे. E hat I स्क्वायर करने के बाद क्या करेंगे? नेचुरल लॉग करेंगे. ln to the base E. Natural log करके you will get all values of natural log of E hat I square. Then you will regress that on theta plus gamma xi. So you will have a new regression where log of sigma E hat I square will be the dependent variable and xi will be the independent variable. Next, estimate the fitted values. So you will get log of E hat I square ka hat of, right, estimated values. After that, raise them to the power E. After that, you raise them to the power E. Once you have raised them to the power E, what will you get? You will get estimates of sigma hat I square. Once you get the estimates of sigma hat I square, divide each value of y and x by the square root of these. So divide y1 and x1 by square root of sigma hat 1 square. Divide y2 and x2 by square root of sigma hat 2 square, and so on and so forth. Right? Okay? Then, what's the next step? Then next step क्या होगा? Run a regression of the modified values of y on the modified values of x. Right? Which will give you beta hat FGLS and alpha hat FGLS. But we are not really worried about beta hat FGLS and alpha hat FGLS. Because our original alpha beta were consistent and unbiased anyway. So if alpha hat FGLS or beta hat FGLS का कुछ ज़्यादा लेना देना, we are not particularly enamored of that. Why we want to do it is, we want to get the correct standard errors. So we want to form the standard errors from this equation, which will be sigma hat square v upon summation xi star minus x star bar this whole square. So instead of xi, you will be using xi star. Right? And then you will form the t values and all that, where your tests of hypothesis will now be correct. Right? So we do this feasible generalized least square. We do all GLS not because we want the parameter estimates. Our parameter estimates to OLS is also fine. We do GLS because we are concerned about the incorrect standard errors. We have to get correct t values and correct tests of hypothesis. Sure? Everybody has understood this? So quickly tell me why this is called weighted least squares. Each value of yi and xi is weighted by 1 upon sigma I. If all the sigmas are the same, then you just have the OLS. Right? If the sigmas are different, then you in a sense have the weighted GLS, weighted least squares, which is also a formula for the generalized least squares GLS. Right? Which is also a formula for GLS. Everybody's got this? So any doubts about this? Yeah.
Weighted least square and GLS is same.
Yeah. So generalized. So okay. So that's an interesting question. Is the weighted least square and GLS the same? Can somebody throw light on this?
But it will be of the population. So this has to be a consistent estimate of the weighted WLS. That's a consistent estimate of what GLS will be if you know each and everything.
Anything more?
In general, these squares we are also explaining ordering these squares as well as this, because we are saying that 1 upon sigma, if the sigma is same, it won't stand. Whereas in weighted least squares, if we are bringing the entire aspect of sigma, we are changing the entire thing. So I feel there is a difference between them.
Anything more? See, GLS is a general strategy. For example, if you have autocorrelation, then you do a GLS in a certain way. You do yt minus pi hat yt minus 1 as y star. and xt minus phi hat xt minus 1 x star. So if you have autocorrelation, you will do GLS in a particular way. If you have heteroscedasticity, you will do GLS in a particular way. So if you do GLS in a particular way when there is heteroscedasticity, you get WLS. So WLS is nothing but an application of the idea of GLS to heteroscedastic model with heteroscedastic disturbances. That is, you divide each of yi and xi by sigma I, then you get a weighted least square. So weighted least squares is one particular application of the generalized GLS idea in the context of heteroscedasticity. No, but because we don't know them, we worked out a policy strategy for getting an FGLS. No? So because we do not know sigma I square, we have found a strategy for estimating sigma I square. Right? Everybody get this clearly? Sure? Any doubts? No? Okay. So now we have learnt how to correct for autocorrelation if there is autocorrelation. How to correct for heteroscedasticity if there is heteroscedasticity. Now we go back to the original question. When will I correct for autocorrelation? If there is autocorrelation in the data. Right? If there is no autocorrelation in the data, then I can't really correct for autocorrelation. Because if I still go ahead and correct for autocorrelation, if there is no autocorrelation in the data, what's going to happen? So the point is, I need to be able to know whether to correct for autocorrelation. Right? So I will need to know whether there is actually autocorrelation in the disturbance. Similarly, we will ask the question of how do we know whether there is heteroscedasticity in the disturbance. Okay? Now, I want to outline to you a very, very popular test in autocorrelation called the Durbin Watson test in autocorrelation. Okay. Remember, so can this all go? Can this all go? Yeah, this is all looking very nice. So suppose you have a model or say YT. Okay? Sure? So if it's testing for no autocorrelation is equivalent, and I will say the absolute value of phi is strictly less than 1. The absolute value of phi is strictly less than 1. That's another which I am going to make. Why doesn't the absolute value of phi should be strictly less than 1? What would happen if it is 1.6, for example? So the absolute value of phi was 1.6. What would happen? So if ET is 1, ET plus 1 would be 1.6. ET plus 2 would be even bigger. ET plus 3 would be even bigger. So the residuals of your regression keep on becoming infinitely large, which they generally don't. If phi were minus 2, they will keep on becoming smaller and smaller and smaller. Right? On the other hand, if it is 0.8, for example, phi, then if ET is 1, ET plus 2 will be 0.8. ET plus 2 will be 0.8 into 0.8 cube and so on. If there is a shock today, the impact of the shock on those future values will keep on dying off in the, if the value, if phi is less than 1 in absolute value, and that's the kind of a restriction we are putting on the data. Very soon you will realize that has to do with something called stationarity, but we will come to it when we are doing it. Right? The absolute value of phi is less than 1. Sure. Okay. Now, So I want to test the null hypothesis of no heteroscedasticity, which is phi is equal to 0. Yeah? Against the alternative phi is not equal to 0. So we need to test that. Right. So first, consider phi hat. Yeah? What is phi hat? Phi hat can be obtained as this is what we have seen in the last class. Alright? So think of two into 1 minus phi hat. Two into 1 minus phi hat. This statistic has a name. It is called the Durbin Watson statistic. Right? Watson as in the Watson in Sherlock Holmes. Right? And Durbin is D-U-R-B-I-N. Durbin Watson statistic. Yeah? The Durbin Watson statistic. Now the point is, if phi hat is actually equal to, if phi is equal to 0, what value would the Durbin Watson statistic take? 2. What is the maximum value of phi hat? Phi 1. So if phi is equal to 1, what would Durbin Watson take? 0. And if, what is the lowest value of phi? Minus 1. If phi hat is minus 1, what would the value of Durbin Watson take? 2 minus minus 1. 4. Right? Sure? Is the value 4. So the Durbin Watson lies between 4 and 0. The closer is the Durbin Watson to 2, the lower is the evidence against the null hypothesis. The closer is Durbin Watson to 0 or closer it is to 4, greater is the evidence against the null hypothesis. Yeah, greater is the evidence against the null hypothesis. Is it clear? Closer Durbin Watson to 2, greater is the evidence, weaker is the evidence against the null hypothesis. If the Durbin Watson is close to 2, weaker is the evidence against the null hypothesis. If the Durbin Watson is close to 0 or close to 4, greater is the evidence against the null hypothesis. Now, what kind of a distribution do we compare it? What kind of a distribution do we compare it? Right? The point is, this distribution depends upon what are the explanatory variables in the regression equation. So, the number of explanatory variables in the regression equation change, then the distribution with which you compare the Durbin Watson statistic also changes. Right? That's the whole point. And therefore, Durbin and Watson actually have given us the upper and the lower for each number of explanatory. You have two explanatory variables. There is a certain number of upper, there is the upper limit and the lower limit. If the Durbin Watson is lower than the lower limit or higher than the upper limit, right, you say that you reject the null hypothesis. Right? If it is very close to 2, you fail to reject the null hypothesis. Right? Okay, so it's that kind of a structure for testing for Durbin Watson. But actually, the upper and lower limits have become increasingly irrelevant because R will generally find the Durbin Watson distribution, and software programs will now tell you, it will tell you what the p value is if you reject the null and so on. So the upper and lower bound used to be previously when people had to actually calculate those distributions. Now computers do that, so that's not such an issue. So this is the basic idea of testing for the Durbin Watson statistic. Right? That's the basic idea for testing for the Durbin Watson test. Right? Sure? So, any difficulty about the Durbin Watson test? See that there is no fixed distribution for Durbin Watson. The critical values, the distribution depends upon the number of explanatory variables in this equation. So the number of explanatory variables in this equation change, the distribution, the limit in the sampling distribution also changes. So therefore, what Durbin and Watson have done is, for each set of number of explanatory variables, they have given you certain critical values. You know, if the Durbin Watson statistic lies outside those boundaries, you reject the null and so on. Increasingly aware, you don't need them, because computer software will automatically, if I say you take a Durbin Watson test on this, then you will be able to see, your computer will tell you what's the p-value and all that, right? Okay, so that's something. But the basic idea of Durbin Watson is clear, right? It's a test for, remember, but it's only a test for first order autocorrelation. That is, ET is equal to phi ET minus 1 plus VT. If ET depends upon ET minus 1 and ET minus 2, you have second order autocorrelation as well, then you cannot use the Durbin Watson. You cannot use the Durbin Watson statistic in that case, right? Other case where the Durbin Watson statistic becomes invalid is when you have so instead of xt, you have one period previous value of yt. So for example, yt could be sales in month P, yt minus 1 could be sales in the previous month, sales in month P depend upon sales in the previous month. Right? It's a model with a lagged independent variable. Now remember, whenever you have models with lagged independent variables, OLS becomes a problem. Can you tell me why OLS will become a problem if you have lagged independent variables? If you have lagged independent variables, OLS will definitely be a problem. Model is going to be a problem. Why would OLS be a problem? Endogeneity. Perfect. You see, what can happen is, yt is not a fixed variable. Yt is not fixed. Why yt is not fixed? Because yt depends upon et. So yt is a random variable. If yt is a random variable, yt minus 1 is also a random variable, just one period past value of yt. So if this is a random variable, like if xt is a random variable, et is a random variable, I have no way of ensuring that covariance xt et is equal to 0. In fact, in this case, yt and et are correlated, yt and yt minus 1 are also correlated. So in all probability, yt minus 1 and et will be correlated. Right? So if this is the case, then obviously you can't use OLS. But if you still go ahead and use OLS and do the Durbin Watson test, then it can be shown that the power of the test is low. What do you mean? That it fails to reject the null hypothesis. When will it fail to reject the null hypothesis? If the value is around 2. So if you have the lag dependent variable, the Durbin Watson statistic is biased towards 2. The Durbin Watson statistic is biased towards 2 if you have a lag dependent variable, and therefore that's not applicable. The Durbin Watson statistic cannot be used in a case where you have a lag dependent variable. In such cases,